think we live. We live. Hello everyone. Welcome to the OneClass channel. My name is Millan and I am a software engineering student at Carleton University in Ottawa, Canada. Today we'll be going over some commonly asked physics questions at both the high school and early university level or college level. If you need some help with your tutoring, if you need some help with your homework, or if you're interested in tutoring, check out the links in the description below. Cool. I'm gonna just switch over my screen real fast. Okay, cool. Let's start the party. Okay, cool. So, the first question that we got on the menu today is how do we convert centimeters to meters? So, 1 centimeter equals how many meters? So the key here is our prefix. Let's think about all of our prefixes. Some of them are most likely going to be kind of familiar to you. So we got T, G, so we have tera, giga, mega, kilo, centi, and then going kilo, and then it's heka, and deci. These are fairly uncommon. And then like this is 10 to the 9. Whoops, no. Let's actually go the other direction. I know kilo is 10 to the 3. Mega is 10 to the 6, giga is 10 to the 9, and tera is 10 to the 12. You might recognize these words from like, your memory cards. You got terabytes, gigabytes, megabytes, and you know that they're like, each one is 1,000 times bigger than the previous. So this is what you would use for your SI stuff. And like this is like 10 to the 2, and this is like 10. But these are like very rare. So we might as well just ignore them. Now go in the other direction, if we're going small, so let's just like 1, 10 to the negative 1. That's actually so uncommon that it's like, I'm not even gonna like bother mentioning it. So we have 10 to the negative 2, 10 to the negative 3, then 10 to the negative 6, 10 to the negative 9, and typically you won't see stuff smaller than that. So 1 is just like, you don't have any prefix. This one would be centi. This one would be milli. My name is Millan, by the way, and milli is my favorite because it's a milli. This is micro. The symbol for that is this. Oh, I might as well just draw that. So that's big T, that's big G, big M, that's the K. Centi is C, milli is lowercase m. Don't get mega and milli confused. Uppercase, lowercase, that matters a lot. Micro is mu. It looks like a U, but you got like, those arms on both sides. And the last one, this is nano. And the prefix for that is N. Okay, so to do this, these are just like our base SI one. These are the most like commonly used one. So what's good to do is like if you have like 1 centimeters, you know that centimeters, C for centimeters is equal to 10 to the negative 2. So you can just do like 1 times 10 to the negative 2 meters is equal to 1 centimeter. And if you make that look a little bit different, it will be 0.01 meters. And that makes sense. We know that you ever seen a meter stick? A meter stick has 100 centimeters on it. So if we multiply this one by 100, we would get 1 meter. So 1 centimeter has got to be 1 meter divided by 100. So yep, just keep in mind your prefixes. And it's always good to convert your prefixes into numbers because these prefixes can make your units a little bit uncomfortable to use. Okay, so yeah, you just pretty much divide by 100, which is the same as multiplying by 10 to the negative 2. So the above solution is correct. is correct. Additional commentary on SI prefixes. SI stands for Système International. You know, French people are cool, and we have this like international system that we use to kind of coordinate all the prefixes and units that we're going to use. Yep. Thank you, French people. Yeah. Additional commentary on SI prefixes would be helpful. Okie dokie. Cool. So we can keep it moving to the next question. Okay, the next question, I really like this question. The next question is asking, find the radius of the Earth in meters. Now, there are a couple of different ways that we can solve for this. Like the answer that the junior tutor had given is, you know, if we know the diameter, we can find the radius. Well, you know, if they give us the diameter, they probably won't ask us for the radius. There are many different ways to do this. I think my preferred method to handle this would be to use the actual definition for meter in the first place. Okay, so we know the Earth is pretty much a globe. It's pretty much a sphere, meaning that I could kind of draw it as a circle like this. And yeah, so up here we have like the North Pole. That's where Santa lives. And around here we have the equator. That's where Ecuador and Equatorial Guinea are just some countries that have equator related in their name. Fun fact with geography. The original definition of 1 meter was made by the French people in France. And they said that 1 meter is the distance here. Whoops. This arc distance, let's call that S. And it's the distance from the equator to the North Pole. We'll just call that distance S. And they said the original meter is oh, and you know, because it's the French, they said it has to intersect with Paris. It's up there. They said 1 meter is equal to the distance S, which is the distance between the equator and the North Pole on a line that passes through Paris. That divided by 10 million. Yeah. 10 million. Okay, so let's actually think about this for a second. So the distance between the equator and the North Pole, that's actually like pretty much a quarter of a circle. Okay, so a quarter of a circle, I'm actually just going to move this word equator. Oops. Might as well just, you know, clear that out. So you see here, I'll actually draw this in a different color. Let's make it blue. That's purple, but that's okay. So we know that this angle is about 90 degrees. We know that S is about 90 degrees, and we know that S is 1/4 of the circumference. And what's the circumference? Circumference is 2 times pi, I think. Or is 2 times diameter. No, is pi times diameter. So, which is also equal to 2 times pi times r. So S is equal to 1/4 of the circumference, which is 2 times pi times r. Okay, so we can take this equation for S and input this into the S on our original equation. 1 meter is S divided by 10 million. So 1 meter is equal to 1/4 of 2 times pi times r over 10 million. Or instead of writing 10 million, I'll just do 10 times 10 to the power of 6, because 10 to the power of 6 is 1 million. 10 times that, 10 million. Sounds about right. Okay, now we have basically all the ingredients that we need to solve for r. Okay, and this is just based off the original definition of what a meter was. Okay, so we can multiply both sides by 10 million to neutralize the 10 million on the downstairs of the fraction. And let's isolate r. So r is the only variable that we're trying to solve for here. So we're going to have like 1 meter. Multiply that whole thing by 10 times 10 to the 6. Could have wrote 10 to the 7, but you know, it is what it is. Divide that whole thing by pi. And oh, that 2, this 2 right here, this 2, I can 2 divided by 4, that will just be a 2 on the upstairs there. So it's just going to be a 2 on the downstairs here. Or yeah. Actually, no. No. Actually, like rewrite this to be like, you know, a little bit more proper and clear. This should be S is equal to 0.5 pi r, and instead of up there, I'm going to rewrite that as 0.5. Just like all that fraction stuff does not get confusing at all. 0.5. Okay, so we know that it has to be divided by 0.5. Okay, and this is equal to r. So let's send that through the calculator and find out what our result is. So 1 times, well, I guess we don't need to do 1 times 10 to the power of 6 times 10. So that's 10 to the power of 7. Divided by 0.5, which is the same as multiplied by 2. Divide pi. And that's equal to, r is equal to 6,366 197.724 meters, and that's like the actual precise value that I got from that particular calculation, which is fairly close to what they give here. Now, if I Google real fast radius of the Earth, seems fairly close here. Yeah. Now we do have a little bit of discrepancy here because, of course, the Earth unfortunately is not a perfect sphere, so we are making quite a bit of approximations. But this is how the original meter was defined. Now the definition of meter is changed to be like the amount of distance that that light will travel in a very small increment of time. But originally it was based off of this. The distance between the equator and the North Pole of a line that passes through Paris. Yep. And we see when we do that calculation to find out the radius of the Earth, we can find a fairly good approximation of it. Now here in the answer, they used the diameter. Kind of got to say that If you have the diameter, you would never be asked for the radius. So yeah, if you have radius, taking the radius of the Earth would be better. For example, the original definition of what a meter is. Okay, and actually the reason why they changed the original definition of the meter is because since the Earth is not perfectly circular, we wanted to make it with something that does not depend on a physical thing. Instead, it depends on a universal constant, which is the speed of light and a certain period of time. Okay, so that would be that's the new definition of a meter, and that was yeah, I'm not sure what year that was, but this original definition of a meter, that was a long time ago, way older than I am. I think it was like 1700s or so, maybe later. Anyways, next question that we got on the menu today is derive the spring force equation. So the force of a spring is proportional to how much you compress or stretch it, and that compression or stretching is represented with X, which is compression slash stretch of spring. Okay, now we know that the force of the spring, Fs, the spring force, is not equal. It's going to be proportional to the X, which is the compression or stretch of the spring. Another way that you can mention compression or stretch is the deviation or the distance that the spring is, or the change in distance between its natural rest thing. Okay, and so F of S is proportional to X. Well, let's actually think about like what this means and how we should incorporate our signs here, because signs are kind of important, but they're a lot easier to deal with once you can kind of visualize what's going on here. Okay, so suppose we have a spring like this, like that. Okay, this is its natural rest position, and this is like affixed against a wall. When it's in its rest position, it's how much is it compressed or stretched? 0 meters, 0 centimeters. There's going to be no force here, right? If we have a compression this way, we know that it's going to have a force that goes this way, F. And this distance here is X. And this is a compression case. And if we have a stretch, it's going to look like this. So, we stretch out the spring within its elastic limit, of course. This was its OG position, original position. This is our new X. And our force is now acting in the opposite direction. Now that it's stretched out, it's trying to be like, hey, I don't like being stretched out. Let me, pull myself back together. So its force is going to be this way. Okay. So we can go with the convention that which way you have your X is positive. As like, compression is a negative X, because like we're going closer together. It's like you're reducing the force. You're gonna get a positive, you're gonna have a force in the opposite direction that you're compressing. right? So yeah, it's good to like visualize them first. The official equation is like F equals negative kx. But like these signs can kind of get a little bit twisted depending on which direction that you have. If you have stretch as positive or negative, it doesn't particularly matter as long as you're consistent with it, and if your diagrams agree with it. Your diagrams are quite important. K, that's the spring. This is the compression or stretch, or change in spring length from rest position. K, that's the spring constant. This will be like force per distance. And what that's basically telling you is like how much force is the spring gonna apply under when you have a certain number of compression, like something with a high spring constant, or a large number for a spring constant, would be like the suspensions on your car. Like, because the car is so heavy, it's got a lot of weight force, and to counteract that, it needs to have a strong spring constant, because you don't want to have like a lot of spring compression. Like, you don't want to have like 5 meters. You only want like maybe like a couple inches or it's a couple centimeters of spring compression when you have car shock absorbers or suspension. But like, inside a mechanical pencil, you're going to have a much smaller spring constant, because you don't want to be putting like the entire weight of a car to compress the spring. So high spring constants are strong, thick springs, and smaller Ks are less strong springs. So K is the constant that defines the strength of the spring. And it kind of makes sense with the unit, the force per distance. And the X, that's just distance. Okay, so the signs can really be confusing sometimes, but just make sure that like you can like visualize what's actually going on here, and just like kind of you got to have like a feeling of like which direction would the force be if it's compressed, which direction would the force be if it's stretched out, that type of stuff. But typically, springs are nice to think about, and if you're writing a test with a mechanical pencil, you can just push on your pencil to kind of get some clues on that. So yeah. The above solution is correct. Cool. Okay, next question that we got on the menu today is, how do we define linear momentum? Linear momentum is kind of like a property of something's motion. It's typically going to be useful when you do stuff involving collisions, but just the property itself is also useful for other things, like the official equation for Newton's second law is not F equals ma. It's like F equals like the derivative of momentum, something like that. But momentum is useful for many different things. So the equation for momentum, it's a vector, of course, is P. Now, why does P stand for momentum when momentum doesn't have a single letter P in it? The answer is, I don't know. No one really knows. It's just the convention that we've been using for a long time, and no one wants to go back and undo our bad habits from the past, so we're gonna keep on using them. So momentum, P. Yep, makes sense. Momentum is mass multiplied by velocity. Velocity is a vector. Mass, of course, is just a scalar. You can say like, oh, I weigh 100 kilograms. You don't need to specify the direction, which is why we can keep it as a scalar. Okay. Now the unit for this, well, mass is going to be um, typically, well, it's just going to be mass. And v is going to be velocity. And velocity is distance divided by time. Okay, so the momentum is always in the same direction as the velocity. You can kind of see the momentum as a scaled version of the velocity, but the scaling also includes another unit that changes the properties. So it's not just velocity. Okay, so in Système International, SI units, we would have kilograms times meters per second, not second squared, that's acceleration. We're talking about velocities here. And this is momentum. SI units. And you could see, like, if you took the time derivative of this, you would get a force. And that's why Newton's second law is officially, like, we use F equals ma, but officially it's actually the time derivative of momentum, which is a little bit more interesting. But that typically doesn't really apply until you get into, like, real deep into the physics and you learn about, like, relativistic stuff. But otherwise, this stuff is pretty cool. Yep. And yeah. Above solution is good. Awesome. It's a beautiful thing. Beautiful thing. Okay. Just gotta check something super fast. Okay. Okay. We good to keep it moving. Next question that we got. Ooh, I like this question. Why does ice float? This kind of gets a little bit into chemistry as well. So let's talk about, why do things float in the first place? Things float when the buoyancy force is greater than the gravitational force. Oh boy. Buoyancy force is greater than weight force. Buoyancy force comes from changes in, or comes from the difference in density, or exists when a thing of interest has lower density than medium it lives in. Okay, so the buoyancy force, let's think about this, okay? Beach balls. Beach balls are super fun, but they don't float away like helium balloons, right? Because their buoyancy force is less than their weight force. Of course, beach balls weigh a little bit of something, but their density is actually more than the density of just regular air, because of course there's like the plastic that makes up the actual ball. But you take a beach ball for a swim, the density of the beach ball is much lower than the density of water, right? Well, you know, think about that for a second. Density is weight divided by volume. Like 1 square meter of beach ball is going to be a lot lighter than 1 square meter of water, or 1 liter of water, or 1 liter of beach ball is going to be a lot lighter than 1 liter of water. Try that out for yourself. A beach ball is going to be, you know, a couple of grams maybe, and a liter of water, that's going to be a whole kilogram. They could be about the same volume, but which is heavier, right? That tells you a lot about the density. Floating happens when the density of the item of interest, in this case, why does ice float? Ice would be our item of interest, and it floats, assuming in water. It might not float in other substances like oil or like gasoline, but that's a whole nother stuff. Ice floating in water means that ice is less dense than water. Ice density must be less than water density. Okay, now because ice density is lower than the water density, that means there's going to be a buoyancy force that is like the force of floating, and that's going to overpower the weight force. Okay, now why does ice have... So the easy answer is that ice is less dense than water. That's why. But that's actually kind of confusing, right? Because typically when things go from liquid state to solid state, they get more dense. Like air, for example, or nitrogen is a lot more dense in a solid state as opposed to like liquid state, or because like the things are closer together. But water is a little bit different. So water has a little thing going on called hydrogen bonding. So water, H2O, looks like this. So we got oxygen, the O, attached in like a Mickey Mouse pattern to hydrogens. When water is in liquid form, those like, they're just chilling like this. They don't really have much order to them. They're just free to flow around, move around, bump into each other, and all that. So this would be liquid. And here we have like no real order. When it gets cold, these like water molecules don't really want to move around as much. Actually, the measure of temperature is really just the average velocity of all the particles that are contained inside. Fun fact. But as it gets colder, these water molecules are not really bouncing around as much. They're going to kind of crystallize. And they're going to crystallize in a pattern like this. So there's going to be like that. Yep, so they're going to kind of like bond in a crystallized, very ordered pattern like this. Now, the way that their pattern works when they are crystallized is when they're crystallized, they're not able to like hug each other. Like imagine, you're in a room with a bunch of people. If everyone's just like dancing around, you can be like kind of close to each other. But if they say like you have to get ordered in this particular way of like, you're holding onto the shoulders and your arms are completely stretched out, like you're going to have a higher density or a lower density of people. People are going to be more spread out if you force them to arrange in this type of pattern. They're kind of like sticking their arms out and saying like, you cannot get closer than this to me, or because otherwise we're not going to maintain the proper structure. So this in a solid, the hydrogen bonds make crystal structure. Okay, and because of the hydrogen bonds making the crystal structure, it's less dense. Than liquid state. Okay, now interesting thing about hydrogen bonding and the fact that ice floats is that if ice didn't float, we probably wouldn't exist. There'd probably be no life on Earth, like period. The reason why is because, well, think about when it gets cold outside in the winter, the water that freezes into a solid state flows to the top. If the water that froze and became ice was sinking to the bottom, it would be impossible for any plants at the bottom of the ocean to like grow. Like you can't really grow plants inside of ice. So because the ice freezes and like, is like the ceiling of the ocean, it allows the plants to like continue to grow at the bottom of the ocean, which is really just laying the foundation for like animal life and more complex animal life to evolve over thousands and thousands of years. So Shout out to hydrogen bonds for making ice float and allowing us to live by not killing all the plants real far back in the history. Yeah. Okay. So this solution is good. Enhanced with dimensions of buoyancy force. Cool. Yeah, water. Water is my favorite liquid. Okay, so the next question that we got on the menu today is, what is the significance of the conversion of potential energy to kinetic energy and kinetic energy into potential energy? Okay, so the significance of the conversion between them is that we first want to use one of the most fundamental laws of the universe, the conservation of energy. Conservation of energy basically tells us energy, let's just call that E, energy, E, yep, sounds reasonable. E cannot be created or destroyed. Only moved from one place to the other. Or not, maybe not moved, transferred. Now, it's kind of convenient to think of energy not as like a thing, but more as like a property of a something. If that kind of makes sense. Like, you could kind of think of it as like a currency. So like, if I'm losing potential energy, I have to give it to someone else. And that type of stuff. Okay, so... here in the solution that the junior tutor gave, we got a couple of different examples of some different energy equations, right? So we can do like EK, or let's call this kinetic energy, 1/2 the mass times velocity squared, rotational KE for rotational kinetic energy, we got 1/2 I, which is the moment of inertia. Basically, that's like how difficult it is to rotate something, multiplied by its angular frequency. Some other classics that we like is gravitational potential energy. So grav potential E is equal to mgh. And elastic potential energy, elastic PE, is equal to 1/2 the K, which is a constant, times the compression, which is D. Also, sometimes you might see it as 1/2 kx squared. X is equal to D, which is equal to displacement of spring and elastic. They're kind of like, you can kind of use them interchangeably. Even like, well, if you think about it, an elastic band, you stretch it out, it tries to return to its original state. If you have like a spring, it's going to do the same thing. It doesn't really matter what is supplying that force. It just, how that force is supplied, and it's elastic. Okay. Of spring from rest position. Now, why do we sometimes write it with D and sometimes write it with X? Sometimes we need to have D to represent other properties, like distance. Like if you're trying to say the distance traveled. If I have a slingshot, I stretch it out initially. It has potential energy, no kinetic energy, because I'm just like having it like chambered and ready to go. The moment I let go, the potential energy in the spring is gonna like reduce itself because it's returning to its original state, in its original like unstretched out state. There's gonna be no potential energy, but all that potential energy in the spring is converted into kinetic energy of the projectile of that slingshot, and you might need to calculate like the distance that it will travel, given certain like frictional conditions. Okay, so kinetic energy and potential energy are extremely related to each other because the sum of both of them is always going to be the same. So E total is typically going to be equal to the sum of potential E plus the sum of kinetic E, and this equation is always true. Yeah. So a nice example that we can use to talk about this is a basketball bouncing, and we're gonna assume that it never loses any energy on the bounce. Okay. I'll actually draw out its like height pattern. So if we have like this is a height and this is time, bouncing ball, approximation, let's say we started up here, we drop the ball, it bounces a little bit, bounces, and it's gonna like the height of the bounce is gonna like keep on getting smaller and smaller and smaller. Okay, so initially, if I'm just holding a ball, like imagine this is a ball, it's a circle. If I'm just holding it here, it has no kinetic energy because kinetic energy is mass times velocity squared. No velocity, no kinetic energy. But it does have potential energy because I'm holding it above the ground. And at a moment's notice, I can drop it, and as it falls, its potential energy is decreasing. And the amount that the potential energy decreases by is the same amount that the kinetic energy is going to increase about. So the amount of lost potential energy is always equal to the amount of gained kinetic energy. Then it hits the ground, bounce. When it bounces up, it actually lost some energy in the bounce because some of the energy is going to be in the sound, right? So the kinetic energy, some of it is converted into heat, some of it is converted into sound. So there's less energy overall. And then as it bounces up again, you should expect it to get less high because it has less potential energy because some of the original potential energy was converted into kinetic, and then that kinetic lost some energy through heat and sound of the bounce. So on its way back up, it'll have less potential energy. So like situations like these, you always got to consider like the potential energy, kinetic energy, how do they relate to each other? In like a gravitational situation like this, mgh is what you really want to have as a variable of interest because it will always change. For potential energy and kinetic energy, you have 1/2 mv squared. So the v is going to be your parameter of interest or your variable of interest because v is going to be always changing. Like at the peak of its bounce, it's going to temporarily have like a vertical velocity of 0 because like it used to be going up and then it's going down. For like just a brief moment, it had to have a velocity of 0, and at that point when the velocity is 0, all of the energy in the entire system is in potential energy, so that's mgh, and that will be when h is at its highest. So yeah, that would be the significance of the conversion of potential and kinetic energy. Number one thing you got to remember: conservation of energy. Energy does not come from nowhere. It has to come from somewhere. The amount of energy in the universe is a constant. Kind of. Think about that for like, of course the scientists are trying to prove that wrong, and they kind of already have, but for the purposes of most mechanical situations that you're going to study in physics, assume that the amount of energy in the universe is always constant and always the same number. Conservation of energy, important stuff. Just know that potential will become kinetic and it'll go back and forth. Yeah, and I guess they also talk about a little bit about deformations and that type of stuff, but for collisions. So when collisions occur, the act of actually deforming stuff actually takes energy. So that is going to absorb some of your potential energy. So your kinetic energy will not perfectly like line up with it. You also have to consider like things like object deformation or friction from bouncing and like the sound that it might create, those type of things. But you know, if there's missing energy, there's always going to be some factor for like friction related that will account for that missing energy. Okay, so the above solution is correct. Awesome. Next question that we got on the menu today is, how do we calculate speed? Now, you know, we got the need for speed, and let's think about like in a car, how do you measure your speed if you're in need for speed? Well, we have our speedometer, and our speedometer tells us how fast we're going in either kilometers per hour, kilometers per hour. Sometimes we have miles per hour, or I think miles per hour is like mph. Regardless, it seems that our speed measurement is always going to be some distance value divided by a time value. Okay, that would be the units of our speed. And based on the units, we can use the units to kind of help tell us what the equation or how we should calculate it. So if you have distance divided by time, that's really what we need to find out how to calculate the speed. Okay, so maybe for example, you're taking a walk and you walk 10 kilometers in 5 hours. You take a walk, you do 10-kilometer walk in 5 hours. Maybe you're walking slowly. If you wanted to find the speed, well, you would just take the distance value, 10 kilometers, divide that by the time amount, that'd be speed. Divide that by the time amount, which is 5 hours. And you would have like, well, 10 divided by 5, that's 2. That's 2 kilometers per hour. Okay, so to find the speed, you just want to take the distance that you travel and divide that by the amount of time that it takes for you to travel that distance. If you're super fast, if you're the fastest kid around, and you do like 10 kilometers in half an hour, well, then you'd be going 20 kilometers per hour, because you do 10 divided by half an hour, 10 divided by 0.5 hours, 20 kilometers per hour. So that would be like a different example. So you just got to take your distance that you travel, divide that by the time it takes you to travel that distance. That's how you get the speed. If you got the need for speed indeed, and you will succeed if you use these equations, if you know what I mean. Yeah. Cool. So the above solution is good. Examples would be helpful. Okay, cool. Now, the next question that we got on the menu is, how do we find the instantaneous speed? Okay, so in the previous example, we were, let's say we were talking about like average speed. We were talking about average speed is like how much distance you travel divided by how much time you do. Like if you're going 5 kilometers in 1 hour, you're going 5 kilometers per hour in terms of speed. But you can't guarantee that you're always going that speed. Like what if you You sprinted for a couple minutes, you took a break, and then you jogged the rest of the way. Like, your speed at different instants of time throughout that path would have changed. Of course, your average speed is going to be a constant value, and it's an average speed is the average rate of, or average, the average speed is total distance divided by the time taken. To find the instantaneous speed, it is a similar process, except we want to do it over like the time taken, so that time taken is like smaller and super small. It's really like the equation that they have here is the limit. You could also write this as like the change in distance, the change in d over the change in t. The change in t. The triangle is the Greek letter delta, which represents change. So the limit as t approaches 0 for the change in distance over the change in time, this is equal to, sometimes you also see limit written like this, lim as t approaches 0. That's actually more common. I don't know how I completely wrote out limit. To do that, you're really just taking the derivative with respect to time of the distance value. It's probably a little bit dangerous to use the d, because you do use the d to represent differentiation. I guess in the solution that the junior tutor gave, they use s. I think that actually might be a better move. Why do we use s? Well, s is frequently used for like distance related stuff. Why? Distance? I think that's why. So you really, to find that instantaneous speed, you want to be using the time derivative of this. Now, you kind of got to be a little bit good at calculus to handle this. But let's say you have a distance function. Let's say you have an s function of t. This will be your distance. Function. It's going to be like some function. You'd want to take the time derivative of this. So let's say your distance function is like x squared. Nope, not x squared. T squared. Your instantaneous velocity is just going to be the derivative of that. So it's going to be d over dt of s of t. It's going to be d over dt of t squared. That's just 2t. Okay, so that's just like a very simple derivative example of like, a distance function and how you could get the instantaneous velocity based on that. Really what you need for this is just to know how to take a first derivative. Now, okay, amplitude. I'm not sure if I cut out there because I got a message that said my stream was interrupted, but amplitude is just like the maximum height of the wave. It is not like the distance between the bottom of the wave and the top of the wave. That would be like your peak to peak voltage. Typically you'll see that in like electrical engineering type applications, but amplitude is just like the distance between your 0 and the highest value. That's the amplitude. The top of a wave, this section, that's called a crest. And the bottom of the wave is called a trough. A nice way to remember like the difference between a crest and the trough is like, the moon. Sometimes there's like a phase of the moon that's called a crest. The moon is up, so you know that crest has to be up. That's how I remember it. And a trough, it's kind of like a cup. It's like a valley. And like animals that eat out of troughs, those are kind of look like valleys. They're like, they're big bowls basically, that are more long than they are circular. That's what a trough is. So yeah, troughs are down low. The moon is a crescent. So moon is up, crests are up. That's how I like to remember it. And the wavelength is the length that it takes for one wave cycle to complete. So if you see like I'll do this in a whole new color. A wavelength here one wave cycle, one wavelength. Yeah, so wavelength is, believe it or not, the length of an entire wave. Just be careful about half waves and full waves. Like it might be tempting to say like just the crest, like just the top part, like up to that point right there. Just that would be a wavelength, but no, it's got to be a complete wave cycle. Basically, just want to like if you have like a wave, just like chop it down to see where you see things repeating. It's gonna go up and down, like that would be one repeat, and just look for the length of that. That'll be one wavelength. Okay. Now this is what we would call like a transverse wave, but you can represent other waves like torsional waves or compression waves. You can represent them with transverse waves mathematically. So that's why like transverse waves are probably the most important to be aware of, but they are not always applicable or common in real life. So an example of a transverse wave is electromagnetic waves. So like light is a transverse wave, but sound is a compression wave. So if this was representing a sound signal, like higher up, like here is going to be like higher air pressure. And this would be like lower air pressure. If it was sound, but yeah, multiple different ways that waves exist, but you want to be very comfortable with your sines and cosine waves to help you accommodate that. Yeah. So the above solution is good. So the next question that we have on the menu is kind of related to the previous one, is what is the amplitude? That is the oops, let me draw out like another graph of a wave. So suppose this is just like a single cycle of a sine wave. This would be the amplitude. Okay, now the amplitude is basically a measure of how intense the signal is at that point. So, let's say we have a sound signal that is not necessarily a perfect sine wave. If you ever looked at like the actual sound signal of like, your favorite song or whatever, it might look like some sections like this, some quieter sections, some louder sections when the bass drops, and then, we got like a little bridge. And then, another bass drop, and then, someone screams over here. So these areas, this would be like higher amplitude. Areas, and like maybe in the green sections, these would be like lower amplitude sections. So like if this happened to be like an audio track, when the amplitude is lower, you're going to expect the volume to be lower as well. For sound waves, amplitude is essentially the loudness, measured in decibels, but more specifically, it's actually a measure of instantaneous air pressure density. Now, when the amplitude is higher, like when you're, maybe listening to a metal song with a lot of screaming, or it's a bass drop, you would expect it to be louder at those sections and higher amplitude. Let's say for maybe a light signal, or if you're putting on a light show, where it's higher amplitude, you would expect to see like brighter lights or dimmer lights, depending on if you're at the top of the curve or at the bottom of the curve. Amplitude is a good measure of how intense a signal is. Okay? Cool. So, yeah. And the amplitude is proportional to the square, or energy is proportional to the square of amplitude. Interesting. I didn't know that. So yeah, the above solution is good. Okay, cool. Now, the next question on the menu today is, how do we calculate the frequency of a wave? The frequency of a wave is essentially like how many times it occurs per second. Like a wave like this, whoops. This would be high frequency. A wave like this would be low frequency. Okay, now let me first introduce you to the universal wave equation. Universal wave equation is F is equal, the frequency is equal to velocity divided by lambda. F, that's the frequency. V is the speed of the wave. And lambda is the wavelength. So frequency is measured in hertz. Let's get that there. In hertz, Hz. That's named after Heinrich Hertz. That's a scientist who was really into electrical stuff. Yeah, interesting. Speed of the wave, that's going to be in base SI, because typically you'd use these more scientific calculations in SI units. Sorry, Americans. Speed of the wave, that's going to be measured in meters per second. And the wavelength is going to typically be measured in seconds. No, not seconds. Whoops. Meters. And I guess a nice clue for that is wave length. Length. Yeah, they're going to need a length type unit. Meters is the appropriate one for that. Hertz. Oh, by the way, hertz is equal to 1 over seconds, or equal to seconds to the -1. But since we use it so commonly and we see it so many times, we actually gave it a whole unit itself for frequency. But keep in mind, it is just 1 divided by seconds. Okay, so if you look closely at this thing, like we would have like 1 over seconds is equal to meters per second divided by meters. Like this perfectly works out to be 1 over seconds equals 1 over seconds. So the units perfectly line up for the universal wave equation as it should. So yeah, using this equation, we could find the frequency of something. So let's think about like a green laser pointer, for example. So we know a green lasers, lights. So this the V would be equal to C. C is the speed of light, which is 3 times 10 to the 8 meters per second. That's pretty fast. A lot faster than I can run. The wavelength, let's say we have like typical laser wavelengths are around like maybe like 500 nanometers. And we could easily convert that into base SI because, you know, we want meters, not nanometers. So we can just convert that nano into a times 10 to the negative 9. So that could just be like 500 times 10 to the negative 9 meters. And that would be our lambda, or our wavelength. So how do we find a frequency based on that? So our F, well, our F is just going to be V divided by lambda. So V over lambda is equal to 3 times 10 to the 8 meters per second divided by 500 times 10 to the negative 9 meters. Let's send that through the calculator and figure out what the answer is. 3 times 10 au pouvoir de 8 divide by 500 times 10 to the power negative 9. And our frequency is going to be 6 times 10 to the 14 hertz. That's a lot of hertz, but it's not going to hurt us. That would be like 60 terahertz. Yeah, because tera is 10 to the power of 12 or 600 terahertz. Anyways, it's probably safer to just keep it in base SI units, like if you keep it in scientific notation, so there's no risk of like fumbling the conversion to prefix. But yeah, that was just like a concrete example of how you could use the universal wave equation to find the frequency of something, of a wave. Okay, so if they give you the speed of a wave and the wavelength, well, think back to universal wave equation. Wavy like gravy. So yeah, the above solution is good. Cool. Example could be helpful. Okay. Oh man, we're done already? Time flies when you're having fun, as the old saying goes. Okay, just prepare something real fast. Cool. So those are all the questions for today. If you enjoyed today's Q&A and would like to be notified of when we do this next, please hit the subscribe button and ring the notification bell below. If you'd like to submit your own questions, also visit the links in the description below. So if you enjoyed the video, please leave a like and leave a comment mentioning mentioning your thoughts. If you really liked the video, share the video with your friends. And this has been Millan with OneClass. I hope to see you again soon. Take care and have a good day or good night, depending on what time it is. But otherwise, stay safe, and physics is a fun